All right, returning to the development of the Newtonian framework prior to 1900, we're going to look at biology with the major exception, of course, of Darwin's theory of evolution, which will show up later in the course. The Aristotelians, who respected observation, were impressed by the difference between between living things and non-living things. And of course, I don't mean to suggest Newtonians didn't respect observation, but Aristotelians took it at face value to a greater extent than Galileans and Newtonians did. And it's very plausible to just think that the world of living things looks and functions very differently than the world of non-living things. The corpuscularian idea that everything is made of matter has a history. It's not obvious. It wasn't a given. So the Aristotelians thought living stuff was importantly different than non-living stuff, which is not to say it was made of stuff other than the four elements, but there were distinctively vitalistic components, things that were part of living things only. So the idea is not that living things are an exception to the corpuscularian approach. And Aristotelians weren't corpuscularians, but they did think that living things were made of basically the same kind of stuff. But they did not think that the chemistry, as it were, of the non-living world would be sufficient to account for what's going on with living things. DeWitt, I think, is not as clear as he might have been, because he's got this oversimple distinction between the mechanical and the non-mechanical. So he gives you the impression that the mechanical approach simply and unproblematically got extended to the domain of living things. He's not wrong, but he is a little misleading. So, as I have mentioned in the previous lecture, the notion of a mechanism gets weakened, most remarkably with Newton's invocation of gravity. But we're not just talking about pushes and pulls as we get to things like chemical and electrical forces. You can posit a force when you've got precise quantitative laws allowing you to predict what's going to happen. You don't have to explain it causally. It gets legitimized when it figures in quantitative precision. So as the Newtonian framework covers more and more ground, the notion of a mechanism gets stretched. The resources of the theory get broadened. So we remember Kepler's metaphor that the universe is like a clock. In many respects, we're starting to see that metaphor come to fruition, but the ways in which the clock operates are a lot fancier than the pushes and pulls that people like Kepler and Galileo had in mind. So we can call this a mechanical conception of the world, but we've got to pay some attention to what counts as a mechanism. It's certainly not contact forces. It may be forces, but the forces themselves are not always super well understood. So electricity, for instance, becomes its own domain. We'll talk about that in a little bit. That's a broadly mechanical conception of how you'd explain part of biological phenomena. But for a while, the mechanisms involved in electricity were very poorly understood. Again, you're not responsible for the names. Galvani first runs an electrical current through the nerves of dead animals and shows that they conduct electricity. Wohler is the first one to synthesize an organic compound from inorganic ones. People have been trying to do that for decades. Notice that when they couldn't do it, that was decent empirical evidence that the biological world was importantly distinct from the non-biological world. But once you can regularly generate organic compounds from inorganic ones, that looks good for the broadly Newtonian framework. So in physics, Newton's own discipline, one of the things that doesn't really get brought out in DeWitt's chapter is Newton's maybe greatest failure as a physicist. He was a corpuscularian. He had a particle theory of light. It came back in the 20th century a little bit, as we're going to see. In the 19th century, it was regarded largely as discredited. There was a competition in France about the theory of light. Excuse me. One of the judges was a guy named Poisson. One of the contestants was a guy named Fresnel. Poisson looked at Fresnel's wave theory and drew from it the consequence that there would be a bright spot at the center of certain optical setups rather than just darkness. And he regarded that as an obvious refutation. It seemed to him very clear that such a thing would not happen. One of the head of the competition, as it were, actually ran the experiment, and it turned out that this consequence of Fresnel's theory was borne out. This is the idea of constructive as well as destructive wave interference. So you get wave patterns. We're going to see this later in the term, where the bright things align, and so you get a bright spot surrounded by dark spots. And so that was powerful evidence that light is a wave rather than a particle. Faraday and Maxwell, as DeWitt does discuss, showed you how to integrate electricity, magnetism, and light as a broader kind of electromagnetic wave phenomena. So the broadly Newtonian approach is doing very well, but Newton's own theory of light is doing very badly. Nevertheless, this is still recognizably Newtonian. Coulomb shows how similar electricity and magnetism's operations are to gravity, an inverse square law. So Newton was finally recognized to have some chinks in his armor, but it's still very much the paradigm governing almost all of the sciences. And so we come to Kelvin's famously misguided speech in 1900, just a few minor clouds on an otherwise bright horizon. We're going to be exploring some of those clouds in detail, but I do want to show you a bunch of other stuff besides those clouds that remain to be discovered in the 20th century. At the time, nobody thought there were galaxies other than our own. That's Edwin Hubble. Marie Curie, the first person to win 2 Nobel Prizes. Her work on radioactivity was just starting to raise questions that will connect up indirectly with some of the stuff we're going to talk about. Kelvin's 2 clouds are going to lead us to relativity, starting next week, and to quantum theory, which is a misleading name because there is no single quantum theory. So the part in this chapter about the black body radiation problem, don't worry about for now. You'll need to look back at it when we start quantum. The stuff about the Michelson-Morley experiment is important. First important point as we get ready for Einstein. Waves were thought to be waves of something. That's a pretty sensible idea, right? So sound waves are waves in air or in water. Excuse me. Waves when you go to the beach are waves of water. So light waves were thought to be waves of something named the ether after Aristotle's ether, though the similarity is pretty much exhausted by the names. And so the idea is that there must be some stuff, and light is a wave phenomenon in that stuff. It's a disturbance in a medium, just as sound is a disturbance in, for instance, air. This connects up to our discussion of Newton and Leibniz on absolute versus relational conceptions of space. If you could measure motion with respect to the ether, that seems pretty much equivalent to measuring motion with respect to space its bad self. So the Michelson-Morley experiment in the late 19th century is designed to measure the Earth's motion with respect to the ether. Look at page 186 of DeWitt if you get a chance. I haven't copied that into this lecture. I'll be doing that example again a little bit in person next week as we get going on special relativity. What you need to take from that example is, as judged from the boat, both swimmers swim the same distance. But they swim different distances if measured from the water. And of course, if you're swimming, what's going to tire you out is how far you swim as measured from the water, not as measured from the boat that you jumped out of. So the swimmer who has to swim farther will come back more tired, and if they're both swimming at the same speed, will come back later than the swimmer who had the same distance to travel as measured from the boat, but had a shorter distance to travel as measured from the water. I think I got those right. So one swimmer has to swim farther as measured from the water. That swimmer you would expect to return later, assuming they're swimming at the same speed. That's supposed to be an analogy for the Michelson-Morley experiment. You shoot off two beams of light and then measure when they come back. The one that has to go farther, as measured from the ether, should come back later. They did this over and over, and the Michelson-Morley experiment is not the only experiment that tries to do this. It was well known at the time of Kelvin's talk that nobody could get the supposed right result, the expected result. The two beams always returned exactly at the same time. That was driving people crazy. Einstein's going to solve it. That's our main launching point for next week. I'm going to add a different sort of swimmer analogy that's a little closer to some stuff Einstein's doing. This is just designed to make the same point. If it doesn't work for you, don't worry about it. Hang in there until I get to teach this next week. Suppose you're in water. I did this with sound waves. I think I borrowed this from a physicist. I don't remember which one. It doesn't have to be sound waves. We could just count waves. Once the wave gets going, the motion of the source doesn't matter, right? The source could pop out of existence and the wave motion that it produced would still be going on. So an observer at rest in the water should detect the same velocity for the sound in all directions. But if she starts swimming toward the sound, or again, if she's somehow counting waves while she's swimming, she'll be catching up to the source in one direction and moving away from it in another. So she won't be measuring the same frequency of sound waves if we're measuring pitch, or she won't be counting the same number of waves if we imagine her first moving towards the source and second moving away. You should count more waves if you're moving toward the source and fewer of them if you're moving away. That's what you'd expect. The Michelson-Morley experiment should detect that difference, and it keeps giving you the same result no matter what. Light, it turns out, will be measured by you as coming at you at the exact same velocity, whether you're running toward it or whether you're running away from it. It is like a fastball coming at you at 100 miles an hour. If you had a lick of sense, you would run away from it, and then it would be approaching you at 100 miles an hour minus the speed at which you're running away from it. Imagine running toward it. Then you would measure its speed as 100 miles an hour plus the speed at which you're running towards it. What's weird about light is if you run towards it, you measure it coming at you at about 186,000 miles per second. If you run away from it, you measure it coming at you at 186,000 miles per second. This is a very strange phenomenon, and it's going to occupy us in our next meeting. Thanks as always for your time and attention.